Hello. This is my title slide. It's a slightly different title slide than you're probably used to. But no, this is actually my title slide. Oh, and actually, I think we have old slides in here, so that's very unfortunate. But anyway, I'm here to tell you to motivate two things. I've got two goals today, which one of them is to give everyone ammunition for why approximations and error can be acceptable, and two, to pique your interest about approximations, specifically sketches, and how they can be used in databases. So going back to this image, look at this, and how much are these cars being sold for? You can actually see the numbers right now, and you'll say there's 5,850 and all that sort of stuff. But actually, there's probably some of you out there that said, you know, there's $6,000. It's simple, it's $6,000. You just rounded it up, and you would go on. It turns out, if you round these numbers up to $6,000, you get a 2.5% error rate on the 5850 and a 1.66% error rate on the 5900, which some people might argue is not really acceptable for other things. Another case where error actually exists is in blood sugar monitoring. If you're a diabetic, like I am a diabetic, I get my blood sugar measured regularly, and I'll go get blood drawn. It'll get taken to a lab, they'll measure it, and that's considered 100% accurate. I can then go to Walgreens, buy a little device that lets me test my blood sugar at home. That is FDA regulated to be 15% error at 2 standard deviations. And yet I use that to make decisions about my health. Now I actually have, there's actually another device that I use, which is, I have a sensor attached to my body that measures my blood sugar every minute. That's also FDA regulated, but it's regulated to be 20% off of a finger prick, which is already 15% off. And so there's a device that I use to control my blood sugar that has somewhere around 35% error, but yet I find value in it in my everyday life. And this just kind of goes into where approximations with humans can actually be very beneficial and very useful. Now, as you get that into databases and so I work at Yahoo, and we work with user audience data, ads, all that sort of stuff. When we start applying approximations in a database, where can it be useful and where can it not be useful? There are some places where it's good, unique users. If it's off by a little bit, whatever, who cares? That's fine. If you're dealing with 500 million users, if you're dealing with 1 billion users and you lose 1 million, whatever, it doesn't matter. Page views, this one as well. You have 100 billion page views, you lose 1 million, you lose 10 million, who cares? It's no big deal. Ad impressions, now I have to start talking to business people because that's revenue data. They're saying, hey, we showed this number of ads that generates money, maybe we don't want to lose that sort of stuff. But at the same time, there are some benefits to doing this. So there's a little bit of settling in when you use approximations. So why are we going to settle? The answer for that is associativity or additivity. We're going to settle because it becomes associative. Specifically, sketches are single-pass algorithms that allow us to do a cardinality approximation in a parallel fashion. We can take it, we can apply a sketch locally on individual boxes and then merge those sketches together and ask it what was the cardinality. We use this for unique users specifically, which is traditionally a problem that requires ON memory based on the number of people. And when you're looking at 1 billion uniques, getting a constant memory and adding some error is a very good trade-off generally. There's a couple of options for sketches if you're interested, if I've succeeded in piquing your interest and you want to learn more about this stuff. Hyperlog is one that we leverage. Some of the properties of it is it has a small memory footprint. You can get about 2% error out of 1 kilobyte of memory, and you can estimate greater than billions upon billions of things with that 1 kilobyte of memory. It has fast unioning operations. One downside is it can't do intersections or disjunction between sets. Some people try to use the inclusion-exclusion principle, but your whole error bounds and everything kind of breaks down when you do that. Another sketch that we use is the KMV sketch, or we use an extension of the KMV sketch, but K minimum values. It has relatively medium error. You can get 1.5% error out of 256 kilobytes of memory. Still constant memory, much better than ON when you're dealing with 1 billion entries. And one of the benefits of this is that intersection disjunction is allowed. With that, I'd like to thank you all and enjoy the coffee.